one of the very powerful methods in studying linear time invariant differential equations is, as well known, Laplace Transform. Okay, and since LTI circuits are described or formulated by linear time invariant differential equations, it's not surprising that Laplace transform is a very useful tool in both analysis and design of LTI circuits. Okay, and soon enough in this course we will see how useful Laplace transform can get, okay, for such purposes, for analysis and design of LTI circuits. But that requires a thorough review of some of the key properties of this transform. Okay, so that's what we will do in this lecture. So we're all more or less familiar with this transform, but let's remember it once again thoroughly. Okay, so we have some signal, suppose that we denote it by f of t in time domain. Okay, and then what we do is, or what can be done is, through some transformation, which we will define soon, from this f of t, another function, this time of variable s, okay, a complex scalar, is obtained. Okay, so this direction, that is from from lowercase f to capital F, we say we go in this is the Laplace transform of f of t, and then if you have f of s, you can inverse Laplace transform it and obtain f of t. Okay, so f of s is said to be the Laplace transform of this time domain signal f of t, and likewise f of t is said to be the inverse Laplace transform of this function in complex frequency domain f of s. Now, before we define the transformation, Laplace transformation, it's important that we emphasize the following: the transformation, okay, Laplace transformation involves two domains. Okay, one, the time domain, whose variable is indicated by this t, the time domain where the signal, okay, f of t is represented by its waveform. F of t, okay, and then we have the S domain, or the complex frequency domain, or Laplace domain. Okay, the complex frequency domain where the signal is represented by its transform. Which is another function, this time in S, our complex variable. Okay. The symbol S stands for the so-called complex frequency variable. Okay, and finally, the Laplace transform of a given time domain signal f of t is defined by the following integral. Okay, f of s, the Laplace transform of a time domain signal f of t, is computed through this integral from 0 minus to infinity, and multiply f of t with e to the minus st. Okay, and all the properties that we will consider in this lecture will be a direct consequence of this this definition or this construction. Now, in order for f of s to exist, f of t should satisfy certain properties, but those conditions, those properties are very mild, and as far as the LTI circuits and the signals involved with LTI circuits are concerned, they are almost always satisfied. Okay, so the integral and consequently the transform f of s exists if the time domain signal f of t satisfies the following properties. F of t is piecewise continuous. Okay, and f of t is of exponential order. Okay, by which we mean it should be able to be suppressed by some exponential function, decaying exponential function. Okay, more formally, we should be able to, for any given f of t, we should be able to find a positive real number, let's call it gamma, such that in the limit as t goes to infinity, f of t e to the minus gamma t is 0. Okay, so even if this function f of t tends to increase, and it can even tend to increase exponentially, but we can always find, if that's the case, even if it's increasing exponentially, we can find a gamma, okay, such that gamma large enough such that the decrease of this piece, e to the minus gamma t, suppresses the tendency to increase of f of t, and in the limit it provides 0. One function, for instance, that doesn't satisfy this property would be e to the t squared. Okay, you can never find a fixed gamma that would be able to suppress this forever. Okay, but luckily we don't have to deal with e to the t squared type signals in LTI circuits. Okay, so these two conditions are almost always satisfied. So that means Laplace transform is a useful tool, is quite applicable for LTI circuits. Okay, so we will therefore always be working with such signals f of t, or waveforms, for which the transform is well defined. In other words, this integral exists. Okay. In particular, we will always let, for f of t's that we'll be dealing with, this limit is satisfied. T goes to infinity, e to the minus st, f of t equals 0. Okay, so having given the construction of Laplace transform, let's begin discovering certain properties regarding that transformation, and also certain transformations of the signals that we're familiar with, like unit step, like exponential function, or sinusoidal functions. Okay, so let's begin by one of our elementary functions, namely the unit step. Example. Let f of t be the unit step u of t. Okay. Unit step function, which has this very simple shape. It's 0 for all negative values, okay, and it's 1 for all positive values, and exactly at 0, well, we didn't bother to define it, okay, so we don't care what it does exactly at 0, but all we care about is that it's bounded at 0, okay, unlike, for instance, the impulse function. Okay, for this function, let us compute its transform. Okay, so what's f of s? F of s equals, let's apply the definition because that's the only thing that we have now, from 0 minus to infinity, u of t e to the minus st dt. So that's the definition. Now u of t for t positive is 1, so let's therefore write this integration as two separate integrals so that we see certain things in a clearer light. This equals the integral from 0 minus to 0 plus u of t times e to the minus st dt plus from 0 plus to infinity 1, because 1 is the value that u of t takes for positive t, times e to the minus st dt. Okay. Now, since, well, e to the minus st is 1 at this, because it's a continuous function, in the vicinity of 0, okay, and we're doing integration from 0 minus to 0 plus, therefore we can consider this as the integration of ut only, because this is 1 in that interval, okay. So what we're doing is we're integrating a bounded function, it can be discontinuous, but bounded function in an infinitesimally tiny interval, therefore this piece will produce 0, okay. Then f of s should equal the second piece, which can easily be computed. What we have is minus 1 over s e to the minus st evaluated from 0 to infinity. Okay. And now, since this one is a continuous function, we don't have to worry about whether this is plus or minus. Okay. And this is, since st goes to infinity, this whole thing is 0. This is 0 minus 1 over s, which is 1 over s. Okay, so we have obtained our first Laplace transformation and time domain signal pair. In other words, Laplace transform of unit step is 1 over s. Okay. Now let's move on to another function, another waveform. This is our second example, which is a very important waveform for LTI circuits, clearly. F of t equals e to the minus alpha t. And suppose that alpha is some complex scalar. Okay, it's a constant. Now again, let's apply the definition, or which is given through the integral. Okay, we integrate from 0 minus to infinity. This guy times e to the minus st. Now, since this is a continuous function, we don't have to worry about 0 minus 0 plus thing, and we can simply put here 0. Okay. So what we have is e to the minus alpha t e to the minus st dt, and that equals from 0 to infinity e to the minus s plus alpha t dt. Okay. Okay, and that equals minus 1 over s plus alpha e to the minus s plus alpha t, evaluated from 0 to infinity. Okay, as t goes to infinity, this whole thing goes to 0. Therefore, what we have is 0 minus 1 over s plus alpha, because at t equals 0, this exponential function becomes 1. Therefore, the Laplace transform of this waveform f of t is over s plus alpha. Okay. Note that since by definition Laplace transform doesn't care about what the signal does for negative times, because the integration is starting from 0 and going in the positive time direction. So that would mean that take the signal, for instance, e to the minus alpha t, and then multiply it with, let's say, u of t. Okay, and its Laplace transform would still be the same, 1 over s plus alpha. Okay, so that's something to keep in mind. Let's now, in our third example, compute Laplace transform of something that's a little bit more extraordinary, namely the impulse function or the delta function. Okay, this is our next example. Suppose that f of t equals delta t, okay? Unit impulse function. Okay. What's f of s? F of s equals, okay, let's apply the definition. Now, since we're dealing with the delta function, we have to be careful about this 0 minus 0 plus business. Okay, so let's put here 0 minus, and what we have is delta t e to the minus st dt. Okay, and this equals, since impulse by definition is 0 for all positive values of its argument, this integral clearly equals the following integration, okay, from 0 minus to 0 plus, because starting from 0 plus to the right, this is 0, fixed at 0, therefore 0 times that is 0, and integral will give us nothing. Therefore, this integration is equivalent to, or is equal to, this integration from 0 minus to 0 plus. Delta t e to the minus st dt. Remember that when delta t multiplies a function, and if that function is continuous, then that product can be replaced by delta function multiplying the value of that function evaluated at the time that makes the argument of the delta 0. Okay, so in this case, the argument that makes delta, the value of t that makes the argument 0 is 0. Okay, so this product therefore is equivalent to, for all practical purposes, the value of e to the minus st at t equals 0, and we gave that property of impulse function a name. We called it the shifting property. Okay, now e to the minus s times 0 is e to the 0, and e to the 0 is 1. Therefore, what we're doing here is we're integrating impulse function from 0 minus to 0 plus. And by definition, that's 1. Okay. Hence, our wild function in time domain, delta t, gives us a very innocent, nice Laplace transform. In other words, its Laplace transform is just a simple one. Okay. Now, again, direct following from the definition of Laplace transform, it's obvious that it's a linear transformation. Okay. So, and that's a very important property for our purposes. And it's almost obvious, but still, for the sake of completeness, let's write it down. By linearity property, we mean the following. Suppose you have two waveforms. Let's call them f of t and g of t. And for each of those waveforms, you have the Laplace transform, capital F of s and capital G of s. And then for the third signal, which is a linear combination of those two signals, f and g, namely AFT plus BGT, A and B are constants. The corresponding Laplace transform simply is the linear combination of the individual Laplace transforms. In other words, this equals A f of s plus B G of s. Okay, A, B constants. Now, let's apply that property, which directly follows from the definition, to this transform that we obtained, okay, e to the minus alpha t equals s plus alpha, to figure out the Laplace transform of a sinusoidal function. Okay. In other words, let's try to figure out sine of omega t, okay? A pure sinusoid oscillating at omega radians per second. Okay. Now we know that sinusoidal functions can be written as linear combinations of exponential functions. So in a sense, sinusoidal functions are exponential functions. And for the sine, we can write it as e to the j omega t minus e to the minus j omega t, and then we have to divide that by j2. Okay, and now we have therefore sine omega t written as sum of two separate exponential functions. Therefore, if we know the Laplace transform of this and if we know the Laplace transform of that, by using linearity property, we can add those two Laplace transformations and obtain the Laplace transform of sine omega t. Okay, so let's do that. Laplace transform of sine omega t equals, first of all, we can take this to the outside the transformation, because we can take this outside the integration. I'm talking about integral in the definition of Laplace transform, and we can write 1 over j2 times Laplace transform of this difference, and Laplace transform of this difference equals Laplace transform of that minus Laplace transform of that, thanks to linearity property. So we have e to the j omega t minus Laplace transform of e to the minus j omega t. Okay, so that equals 1 over j2. Okay, times. Okay, the Laplace transform of this is, we just obtained it. It's this being alpha, it's 1 over s minus alpha. Therefore, it's 1 over s minus j omega. And then Laplace transform of this guy is 1 over s plus j omega. Okay, and therefore this whole thing should be the Laplace transform of sine omega t. Okay, before we write the final answer, let's in order to write the final answer, let's simplify this expression, which we can as follows: j2 times, let's write this as a single fraction. We have s squared plus omega squared in the denominator, and in the numerator we have j2 omega. This j2 will cancel this j2, and we have omega over s squared plus omega squared. So let's put it down. Okay, Laplace transform of sine omega t therefore equals omega over s squared plus omega squared. Okay, now let's move on to an important property. Namely the integration property. Okay, of Laplace transform. This property is the following. Suppose that you know the Laplace transform of some waveform f of t, okay, and then using that transform you can easily write down the Laplace transform of the integral of that time domain signal without actually computing without actually using the definition, okay. In other words, f tau d tau, so this is the integral of f of t starting from 0 minus, okay. And this equals, in terms of the Laplace transform of f of t, simply to f of s over s. Okay, now this is not obvious, okay, to me at least. It's not an obvious property like the linearity property, so that it requires a demonstration, okay. But the proof is quite straightforward, and therefore let's go over it. So let g of t be the integral of f of t, okay, from 0 minus to t f tau d tau. This clearly implies the derivative of time derivative of g equals f of t. In other words, we can write dg equals f of dt. Okay, let's also define this function v of t as minus 1 over s e to the minus st, okay, from which we can easily write dv equals e to the minus st dt. Okay, now using our new notation g and v and applying using integration by parts, we will now obtain easily this property, okay, integration property. So let's do that here. Okay, so we can write L gt equals, remember that this thing is now what we're calling gt, integral of f of t. Now L of gt equals, okay, we're now applying the definition of Laplace transform, this integral minus st dt. So that's the definition of Laplace transformation. Now let's call this part here dv, okay, because we already defined it as such. And then what we have here is the integral of g dv, okay, and then by integration by parts, this must equal gv minus the integral of v dg, okay, integration by parts. Okay, so let's do that and write gv, and v is here minus 1 over s e to the minus st. Okay, and then we're evaluating it from t equals 0 minus 2, t equals infinity. And then we have this integral from 0 minus to infinity v dg. Okay? Okay, so dg is here, f dt, and v is here. So what we have here is, therefore, minus 1 over s e to the minus st ft dt. Okay, this thing here is r v. Okay, and this is dg. Now, integration is with respect to t. Therefore, we can take this 1 over s term outside the integration. And we can write the following. Well, how about this term? Okay, at t goes to infinity, since we have an e to the minus st term here, it takes everything to 0. And at t equals 0, what we have here is, okay, here we have, this becomes 1, and here we have g0 minus, okay. So here, because of this minus sign, we have g0 minus times, divided by s. Okay, so that's the result of this piece. Plus y plus, because we have double minus here, and then we take 1 over s outside the integration. We have this piece, f of t e to the minus st dt. Okay. Now we make two observations here. First of all, this is no other than f of s, by definition, the Laplace transform of f of t. And how about this g0 minus? Now g of t is defined as such, and if you plug in t equals 0 minus, what you're doing is you're integrating from 0 minus to 0 minus. Therefore, independent of the integrand, the result is 0. So this is 0. Okay, and this here is f of s. Therefore, Laplace transform of the integral of f of t is 1 over s times f of s. Okay, and that's the end of the proof. Okay, now let's apply this in order to obtain the Laplace transform of the unit ramp function, because we know that unit ramp is the integral of unit step, and we already know the Laplace transform of unit step. Consider unit ramp. Okay, rt equals t. Okay. Well, to be more formal, we should write rt equals t times ut, but since the Laplace transforms of both of those signals are the same, let's keep the notation simple and consider rt equals t. Okay, now Laplace transform of that constant slope, unity slope line passing through the origin is the Laplace transform of this integral, clearly. Okay, u tau d tau. Okay. Because ramp is the integral of the step function, and we have just obtained the integration property. Therefore, what we can do is we can take the Laplace transform of unit step and divide that by s. So that equals 1 over s times the Laplace transform of u of t, and Laplace transform of unit step was 1 over s. We have another 1 over s here, so that makes 1 over s squared. Okay. Therefore, the Laplace transform of unit ramp is 1 over s squared. In fact, we have the following chain. Okay. We already obtained that Laplace transform of impulse function is 1. And then Laplace transform of unit step is, since unit step is the integral of unit impulse, okay, it's this divided by s. Okay, 1 over s. And then we just obtained Laplace transform of unit ramp is, since unit ramp is the integral of unit step, it's this divided by s equals 1 over s squared. And then we can carry this further. If you integrate t once again, what we have is 1 over 2 t squared. Okay, t squared over 2. This is the integral of unit ramp. Since we are integrating once again, we divide by s once again. So this should equal 1 over s cubed and so on. Okay. That is t cubed over 6 will give you, this is s cubed, excuse me, will give you 1 over s to the 4 and so on. Okay. Now, another property which may become useful sometimes is complex differentiation, and it directly follows from the definition without much work. Complex differentiation. If you have a signal, let's say f of t, for which you know the Laplace transform, and then that signal multiplied by t has the Laplace transform that equals minus the derivative of f of s with respect to s. Okay, and this directly follows from the definition. It's just a one-line proof. And it can be, in fact, generalized easily. Laplace transform of t to the n f of t, okay, n is 1, 2, 3 or something, equals minus 1 raised to the power n. And then you differentiate f of s n many times with respect to s. Okay. Okay, and now let's talk about perhaps the most frequently used property, at least for the LTI circuits point of view, of Laplace transformation. Okay, differentiation in time domain. Okay. Differentiation in and this property we in fact did use when we were obtaining the expression of state transition matrix in terms of Laplace transformation. Okay. This time we will also provide the proof. Now, Laplace transform of time derivative of f of t, okay, f dot of t, equals, by definition, from 0 minus to infinity, e to the minus st f dot dt, okay? So that's the definition of Laplace transform, and now we are computing the Laplace transform of f dot. Now our aim here is to be able to, if we can, express this transformation in terms of the Laplace transform of f without the dot. Okay. So let's call this df and then apply integration by parts. This equals f of t e to the minus st evaluated from 0 minus to infinity minus from 0 minus to infinity f of t and then minus s e to the minus st dt. Okay, so what we did here is integration by parts. Okay, now this equals, first of all, because we have e to the minus st here, it takes everything to 0 as t goes to infinity, and at t equals 0, this becomes 1. So what we have here is minus f of 0 minus. Okay, plus, here we have minus minus, double minus makes a plus, and this s we can take outside the integration because integration is with respect to t. And when we did that, when we did that, we immediately see that this integral is no other than the Laplace transform of f of t. Therefore, Laplace transform of a time derivative of a signal f of t equals s times f of s if the value of that function at 0 is 0. But if not, then we have to be careful about that initial condition. We have to include that in our expression. Okay, and then this can be easily generalized to further differentiation. Okay, f double dot, f triple dot, and so on. So let's also write that down because it may become handy. This is the n dt n, nth time derivative of f of t. Okay, equals let me put it here. This equals Sn f of s if all the derivatives f0, f dot 0, f double dot 0, and so on are 0. But if those derivatives, at least some of them, are not 0, then we have to be careful. And this is the general expression. S raised to the power n minus 1 f0 plus s raised to the power n minus 2. Then initial value of the derivative of f. Okay, then Sn minus 3 f double dot 0. Okay, and so on, plus s fn minus second derivative, and finally plus fn minus first derivative of f there at time 0. Okay, now using what we have just discovered, okay, the differentiation and time domain property, let's figure out the Laplace transformation of our other sinusoidal function, namely cosine omega t. Example. Figure out the Laplace transform of cosine omega t. Remember that recently we obtained the Laplace transform of sine omega t, which was omega over s squared plus omega squared. Now sine and cosine, they have this derivative relation between them. Therefore, using the differentiation property, we should be able to obtain this Laplace transform without applying the definition of Laplace transform. Okay, so what we know is the following. We have that, okay, earlier we obtained the Laplace transform of sine omega t equals omega over s squared plus omega squared. What else? We know that cosine can be written as the derivative of sine equals 1 over omega d over dt sine omega t. Okay, now combining these two pieces plus this property that we have just figured out, we will now write down the Laplace transform of cosine omega t. Okay, Laplace transform of cosine omega t equals Laplace transform of 1 over omega d over dt sine omega t. Okay, That equals, first of all, because Laplace transformation is a linear operator, we can just take that 1 over omega outside the transformation and write 1 over omega Laplace transform of the time derivative of sine omega t. And we know that Laplace transform of time derivative of any function is s times the Laplace transform of the function which we are differentiating, okay, minus the initial condition of that function at t equals 0, or the value of that function at t equals 0, sine omega t evaluated at t equals 0. Okay. Now, regardless of omega, this thing, sine at t equals 0 is 0. Therefore, this term goes away. And what we have here is Laplace transform sine omega t multiplied by s. So we have s omega divided by the denominator. So we have 1 omega, then s omega, s squared plus omega squared. Now these omegas nicely cancel, and we see the Laplace transform of cosine omega t. So let's write them down, because it's a very useful pair to know. Laplace transform cosine omega t therefore is s over s squared plus omega squared. Okay. Now there are a few other properties, and they are not as important as the ones that we have covered, but for the sake of completeness, let's also put them down, and then we can finish our review. Okay. One of those properties is S-domain translation property. By which we mean the following: e to the minus alpha t f of t equals, if you know the Laplace transform of f of t, if you know f of s, then the Laplace transform of this guy simply is f of s plus alpha. Okay, it would be a nice exercise to derive this, which in fact is a one-line derivation directly following from the definition of Laplace transform, that integral. Example. If you have such a signal, e to the minus alpha t multiplying cosine omega t, then f of s equals what? Now, without this e to the minus alpha t term, the Laplace transform of cosine omega t is here. It's just what we computed, s over s squared plus omega squared. And now this property tells us that the Laplace transform of this signal must be this expression here, except that you replace all the s's by s plus alphas. Okay? In other words, we have s plus alpha here and s plus alpha squared plus omega squared here. So that's the Laplace transform of this signal. Another property is time domain translation property. Again, follows easily from the integral definition of Laplace transform. Laplace transform of f of t minus a, u t minus a equals e to the minus as times f of s for positive a. Okay, again, it would be a nice exercise to derive that. let's apply this property to a very simple example. For instance, we already know the Laplace transform of the unit ramp function. Now suppose that we take that unit ramp and move it 2 units to the right. In other words, we obtain this waveform. Okay, so this is here and this is our unit ramp. Okay, 0, and we know that the Laplace transform of unit ramp is 1 over s squared. Now what we do is we take this and we take this function and iterate it, let's say 2 units to the right, and then we're talking about such a signal. Okay. 1, 2, 3, and the slope is 1. Okay. So if this is our f of t, then okay, f of s is, now the f of s for the ramp, the unit ramp, is 1 over s squared, and now we are delaying it 2 units of time, and that delay will manifest itself in Laplace domain by this exponential term e to the minus 2s. Okay, because we have 2 here. And we have the scale change property, which says Laplace transform of f of at. Okay, so that means, for instance, you have some oscillatory, you have some sinusoidal function, let's say, and then with this, which is f of t, and then you consider f of a of t, where you increase or decrease the frequency by playing with the a, and then that projects onto the s domain in the Laplace domain as follows: 1 over a f s over a for positive real number. Okay, again, that directly follows from the definition. It's a very easy derivation. Okay, and finally, let's mention 2 very important theorems regarding Laplace transformation, which links in a peculiar way the f of s and the values that f of t takes at 0 or the other extreme, namely infinity. So we're going to study them under initial and final value theorems. Okay, first is initial value theorem. Sometimes abbreviated as IVT. We assume that f of t is bounded for t 0 minus to 0 plus. Okay, so it's bounded around 0. One obvious example of f of t which wouldn't satisfy this assumption is the unit impulse function, for instance. But if it's not such a function, then it turns out that this limit t0 plus f of t, okay, the value of f at 0 plus equals or can be computed through this limit. Lim s goes to infinity, s times f of s. Okay, and the sister theorem is the final value theorem. Okay, sometimes abbreviated as FVT. To To apply this theorem to a signal, we make the following assumption. Suppose lim t goes to infinity, f of t exists. Okay. For instance, a cosine omega t will not satisfy this assumption because it never converges to somewhere, it keeps oscillating forever. Okay. But if this limit exists somehow, then it can be computed using the Laplace transform of f of t. And the way to do that is as follows. Okay. Limit f of t as t goes to infinity equals lim s goes to 0 s times f of s. Okay. Now, again, these two properties can be shown not directly this time. It requires just a little bit of work from the integral definition of Laplace transformation, and it will be a nice exercise to obtain these properties. Okay, and if you have time and if you choose to do that, here's a hint. It will be it may be useful to obtain these properties, to use this property. Okay, as f of s minus f0 minus equals 0 minus to infinity f dot t e to the minus st dt. Namely, these two theorems follow easily from this time derivative property regarding the Laplace transformation. Okay, so that's the hint for proving these properties.